This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning. So in the last lecture we discussed about the importance of frequency response and finding out a pole in the frequency response or plotting body plots and find out the pole. Then we came up to Miller's theorem. So I'm just going through again. So when you design the amplifier, so the question is, why do you want to find out a pole? Or why do you need a Miller's theorem? Or why do you need a frequency response? So why do you need a frequency response? Without a frequency response, you won't be able to find out bandwidth of the amplifier. So you need a frequency response. Then in order to find out the frequency response, we need body plots. So that's the reason we need body plots. Then why do we need body plots in the logarithmic scale? Because in the logarithmic scale, we can represent the changes, big variations, small variations, everything we can include in the same graph. So that is the advantage of logarithmic plot. That is the reason we are using body plots in logarithmic scale. Then when you have capacitors it is easy to find out pole. Because why do you need to find out pole? Because when you have pole in the circuit, or when you see pole in the frequency response, or when you see pole in the body plots, all are same. Then your gain is decreased by minus 20 dB per decade. So that is not good for your amplifier. So we need to find out the pole. So in order to find out the pole, what will happen is when your capacitor, this capacitor may be due to the transistor, this capacitance is coming. The capacitance also can come because you connect a load. That load got a capacitor or capacitance. Then when the capacitor is connected from a node, so this is a node to the ground, and then if you know what is the resistance, or if you know what is the output RD here, that is collector resistance for BJT and drain resistance for MOS. If you know that values, then we can easily find out what is the pole here. That is equal to 1 by RS into C in. Then pole at the output 1 by RD into CL. So you can easily find out the pole. The pole of a circuit is computed by finding the effective resistance and capacitance from a node to the ground. But the problem arises, suppose you have a capacitor CF that is connected between gate and drain for BJT, base and the collector. This one you may connect externally, or it could be due to the capacitance between gate and drain. There is a capacitance. But when this comes, we don't have a node to the ground. So this is a bit, then without Miller's theorem, can you find out pole? Definitely you can find out a pole for the circuit without using Miller's theorem. Then you have to draw the full small signal and then do the derivations. But then because this one is connected between drain and gate, then your calculation will be a bit tedious. You may need a big sheet of paper in order to find out the pole. So that is the reason Miller came up with an idea that is called Miller's theorem. So what Miller's theorem says is when you have a capacitor that is starting from a node to the ground, see, this is a simple expression, we can find out the pole. So if we can split this capacitor something like this, you have to split between the node to the ground, and then you connect between this node and ground, maybe this node and ground, then we can use something similar so that we can easily find out the pole. So please understand, without Miller's theorem, we can find out pole when you have a floating capacitor. So this is called a floating capacitor because this is not connected to ground. This point is connected to a node, this point is connected to a node. So this is not a floating because one point is grounded, and then this is floating capacitor. Then, so we use a Miller's theorem. The circuit above creates a problem since neither terminal of CF is grounded. So then we can't find out like this. Here it is very simple to find out a pole in the circuit. A method is required that transforms a floating capacitor to two grounded capacitors, thereby allowing association of one pole with each node. So then if we can do something like that, it is easy for us. Then without doing also we can find out, because you might think, okay, without splitting the capacitor, we won't be able to find out a pole. That is not correct. But you can find out, but that is a lengthy and complex process. When you have, this may be a simple circuit, but then when you have a multi-stage or many capacitors, then that can become complex. So that is called Miller's theorem. So Miller what came up with the Miller's theorem, which I already discussed. So when you have a capacitor, what Miller suggested is you split this capacitor into two, and then one you connect it to the ground, then here between input and ground, another one is output and ground. So then what he did is he took the impedance value of the capacitor. So the capacitor CF got an impedance value of ZF. So this point is 1, this point is 2. And then voltage between this point and ground is V1. Voltage between this point and ground is V2. And then this is 1, this is 2. So then what Miller says is this impedance we can split, impedance of the capacitor, or this capacitor definitely we can split it like this. We split it like this. Then if you are splitting, the requirement is, which I already discussed in the previous lecture, if you got X current is flowing from here, so if X current is flowing into it, X current should come out, or 1 milliamps is going in, then 1 milliamps is coming out. So you can split it, then the condition is 1 milliamps is going in. So from here 1 milliamps should go through this Z1 and then come to the ground. 1 milliamps should come here. If 1 milliamps is coming from ground through this Z2 to this point, then that is fine. Then your splitting is correct. But then in order to tune 1 milliamps, then you may have to find out what is the required impedance here, or what is required impedance here, or what is the capacitance, new capacitor value here. We need a new capacitor value. You can't use the same capacitor when you are splitting, because you have to make sure that from this point 1 milliamps is going to the ground, because here 1 milliamps is coming from node 1, and then V1 is the voltage, V2 is the voltage, and then from here it is 1 milliamps is going through this ZF and then coming out here. But here 1 milliamps is going through this Z impedance and coming to the ground. From here, from ground, it is coming out. So then we have to find out then what is the required value of impedance or capacitors. Then your V1 minus V2. So V1 minus V2, because current is flowing from here. This is higher potential. So V1, it is going to V2, because here you are connecting the signal. And then V1 current is flowing from here to here, so the higher potential is V1. So V1 minus V2 by ZF, that is the current flowing this through. That should be equal to V1. So this is a voltage V1 divided by Z1. If you are splitting like that, the same current should flow from this point to the ground. That is the reason V1, because this is a voltage between this point and the ground, this point and the ground. So V1 by Z1. So this is the impedance of this splitted capacitor. If that is true, then you can split it. Then you can find out V1 minus V2 by ZF, which is equal to, then V1 minus V2 by ZF also should be equal to minus V2 by Z2. Means V1 minus V2 by ZF is current flowing through this ZF from 1 to 2. You can split it, then same current should flow from 1 to ground, this point to the ground, so that V1 by Z1. Then same current should arrive here. How the current will arrive here? That should come from ground to this point, so that your V2 by Z2 also should be equal to V1 minus V2 by ZF. We got a negative sign because current is coming from here to ground, so that you are positive V1 by Z1. This negative sign is coming because from here current is coming from ground to this point. So that is the reason minus V2 by Z2. So if you satisfy these equations, then you can split the capacitor into two. Then we can find out from this one, we can write Z1, that is equal to ZF into V1 by V1 minus V2. So why we have written the equation is, conceptually we know we can split it. But then the question is, what is the actual value we need to put in? So we have to find out this Z1 in terms of ZF, or in terms of some circuit value that we can put in, so that we can find out the values. So in order to find out the values, we need to write down the equation. So we got Z1 in terms of ZF, V1 by V1 minus V2. I can write Z1, which is equal to ZF. I can take V1 out and then divide it. Then I can get 1 by 1 minus V2 by V1. But V2 by V1 equal to gain, because voltage between this point out and ground is V2. Voltage between this node and ground is your V1. So V2 by V1 equal to AV. So when you substitute Z1, if you want to split it, this impedance Z1 should be ZF, the actual value, the impedance of this capacitor, divided by 1 minus AV. AV is the voltage gain, low frequency voltage gain. Same way we can find out Z2 from this equation. That is equal to ZF into minus V2 by V1 minus V2. So when you solve, you got Z2 equal to ZF by 1 minus 1 by AV. If AV is the gain from node 1 to 2, which is true, from here to here AV is the gain, then a floating impedance ZF can be converted into two grounded impedances, Z1 and Z2. So Miller multiplication. So what it says is, So we are going to generalize it. When we are generalizing, we are going to represent this as an amplifier, because this is an amplifier, and then you got a capacitor between input and output. That is a capacitor. See, this CF is connected between input and output. So when you generalize, we got an amplifier which I represented using a triangle, and the gain equal to minus A0. That is a low frequency DC gain, like your GM minus GM into RC. That is a low frequency gain. So this is minus A0 is the gain for this amplifier, and then this amplifier, what happens is you got a capacitor connected between input and output. The value is CF, and the gain of the amplifier is minus A0. Means when you connect a delta V signal, here your signal will be inverted because your gain is minus A0, and then you get an amplification. So that is the reason here it is big signal, minus A0 into delta V, because delta V is your input signal. As per Miller's theorem, we can split it. So Z1, so I can split this capacitor into two in order to find out the pole. Z1 equal to Zf by 1 minus AV. Zf equal to 1 by CFS, impedance of this capacitor. S, that is equal to 1 by 2 pi Fc. For sinusoidal signal, S equal to J into omega, which we already discussed in the previous slide. So then what will happen is, we already got Zf, that is equal to 1 by CF into S. What is the gain? AV minus A0 here. So when you substitute, Z1 equal to 1 by 1 plus A0 into CFS, because Zf equal to 1 by CFS. Z2, which is equal to Zf by 1 minus 1 by AV, which is equal to 1 by 1 plus 1 by A0 into CF into S. So then we can split it. Now we will say, okay, our new capacitor will be, what is a new capacitor? Which is equal to CF into 1 plus A0. That is your new capacitor. Because this is the impedance value, then the capacitor is this one. So for V out, CF into 1 plus 1 by A0. So now we can find out the pole here. If you know the resistance here, then we can find out the pole. So what it says is, using Miller's theorem, we can split a floating capacitor into two, and then that two capacitors can be connected from a node to the ground, so that you can find out the pole in the circuit. But then by doing this one, we are also getting some good insight. So the beauty of the Miller's theorem is, obviously that is making our job easy when we wanted to find out the pole. But then this is also giving us some new insight. What is the new insight you are getting? Like you got the Miller's theorem, Miller gave you, and then you read it, yeah, very good, we can find out the capacitor. But then you might be thinking then, okay, so how to think? So when you get something, you should be imagining putting some signal. You know what I meant? You should not be, okay, you got something, but then as a student, what you have to do is, you have to put in some signal and think a bit more. You have to imagine, okay, some signal you have connected. So if I connect a signal, see, I have already connected a signal delta V here, then what is the effect you are seeing? So when you connect a delta V here, for the signal, when you have a capacitor between input and output like CF, the signal will see a very big capacitance at the input. You know what I meant? See, that is equal to CF times 1 plus A0. So for a signal, if you are traveling with the signal, you might think that quickly you can say, oh, signal is coming here. Yeah, signal might encounter maybe this capacitor, maybe if this one got some capacitor, maybe you add up, both are coming in parallel. Not that capacitor. Actually, the signal will see a very big capacitor at the input. So the effect of the capacitor between your input and output, if you got some capacitor, the signal will see a very big capacitor at the input. But then the output, what happens? Output, not much effect. See, only CF, because 1 by A0, if your gain equal to a very big value, this can be neglected. So output is seeing only signal, only CF when you connect a capacitor between input and output. But input capacitor is a big value. It's kind of amplified effect. So that is called Miller's multiplication. So the effect of this capacitor is, for the signal, the capacitance at the input is a very big value. Yeah, so this one, as I said, when your gain is much greater than 1, it is equal to 1 by CFS. As I said here, when your A0 is a big value, you get almost same CF. That is the value of the coupling capacitor. With Miller's theorem, we can separate the floating capacitor. However, the input capacitor is larger than the original floating capacitor. We call this Miller multiplication. So C in, which is equal to 1 minus AV into CF, because we got here plus A0 because your gain equal to minus A0. So that is the reason AV equal to minus A0, you got a CF into 1 plus A0. Example. So we already got this expression. Now how to find out pole for this circuit. So we can split into two your CF, floating capacitor. So you can maybe write from node to C in, and then from output node to ground, that is C in, and then this is C out. So C in 1 minus AV into CF, which you already got it here. Then AV minus GM into RD for this common source amplifier. So you can substitute 1 plus GM into RD into CF. C out, the output capacitance, which is equal to 1 minus 1 by AV into CF, which we already derived by Miller's theorem. Substitute AV equal to minus GM into RD. C out, which is equal to 1 plus 1 by GM RD into CF. So you already got it. So minus GM into RD, and then these are the values. Because as per Miller's theorem, when you split into two capacitors, your C in equal to 1 minus AV into CF, AV equal to minus GM into RD, that is your low frequency gain, and then you got 1 plus GM RD into CF. C out, capacitance at the output, 1 by 1 minus AV into CF, so you got minus GM into RD as AV, and then you can find out now what is a pole, which is equal to 1 by RS into C in, which is equal to 1 by RS into C in is this value. Again, omega out, your output pole, 1 by RD into C out, which is equal to 1 by RD into 1 plus 1 by GM RD into CF. Then, there is a problem with the Miller's theorem. So you found out these poles, and then now you can easily find out the effect of the pole. But then the problem is Miller's theorem is good. You can see here your gain. So as per Miller's theorem, when you split your capacitor, so this Miller's theorem is great. It is simplifying the problem of finding out a pole when there is a floating capacitor. But then Miller's theorem also is an approximation. Why it is called an approximation? But acceptable approximation. So it is almost accurate. Why it is called an approximation? Why? Because you have connected a capacitor. So this is a floating capacitor. When you have a floating capacitor, then you split it into two. One connected from a node to the ground, another from node to the ground at the output. But then, as per the equation, there your C in should be 1 minus AV into CF. You know what I meant? But then AV equal to, you are taken minus GM into RD. But can you take minus GM into RD when you have these two capacitors here? Then you are not taking the effect of these capacitors in the gain for Miller's theorem. You know what I meant? Because here minus GMRD is not actually accurate. It should be minus GMRD, maybe some parallel with the impedance of this one. You can find out as we did. But Miller is not taking into effect that one. Why? Because if you take into account the effect of these capacitors in this expression, then Miller's theorem also is going to be complicated. Then it is better not to use Miller's theorem and then find out the pole straight away from the circuit. But then, is it wrong to find out gain using this expression? If you are operating in the low frequency domain, this is correct. So you don't have to worry about these capacitors. So Miller's theorem requires that a floating impedance and voltage gain be computed at the same frequency. In the what it says is this is low frequency. So whenever you have a capacitor in the gain, the capacitance is a frequency dependent. You know what I meant? So in order to find out, you should be finding out at same frequency. Otherwise you can't find out your gain. See, for example, omega out, which is equal to 1 by RD into C out, and 1 by RD into 1 plus 1 by, then our assumption is this GMRD. The gain is computed at the same frequency as your capacitance, at same frequency. Then here we use a low frequency gain GM into RD. See, Gm into Rd, not Av equal to, so if you take into account, say, if you take into account the effect of this C out, your gain equal to minus Gm into Rd parallel 1 by CLS, impedance of this capacitor, which we are not putting here in the Miller's theorem. Because Miller's theorem is only taking this as the low frequency value. The more accurate result will be when you put minus Gm Rd parallel 1 by CLS instead of this minus Gm into Rd, because you got a capacitor here. But in the Miller's theorem, we are not doing that one, because at the low frequency, even if you put in this one, you get almost same result. And then if you put in another problem is then your Miller's theorem will be more complicated. So it is better to straight away solve this problem from this floating capacitor. Here for the purpose of finding high frequency poles. So even Miller's theorem is not using even this expression even if the circuit is operating at high frequencies, because you still get an approximate value. So Miller's theorem is still good. Then pole identification example, which we already discussed so in the previous lecture. So what we will be doing is, this is 1 by Rs into Cin, this is equal to 1 by Rd into Cl. Then using small signal, we can get what is V out, output current into R out, then this is expression. So this is what we are discussing. So when you find out the gain, then we are not taking the effect of this 1 by CLS in the Miller's theorem. So that is called a Miller's approximation. So here we use the low frequency gain GMRD, not this value, like what we got here. So that is called a Miller's approximation. So Miller's theorem is called a Miller's approximation because we are taking only the low frequency value minus Gm into Rd, not taking into account the effect of this capacitor, which we already derived in the previous slide and in the previous lecture. GMRD, not this big value, which involves the capacitor. Even for the purpose of finding high frequency poles, this is called a Miller approximation. Without Miller approximation, Miller's theorem would be no simpler than the direct solution of the circuit's equation. So that's the reason Miller's approximation. So it's a Miller's approximation. If you put in this value, then Miller's theorem will be complicated. Due to the approximation, there is also another problem. The circuit in the above example exhibits 2 poles instead of 1 pole. Because as per Miller's theorem, when you have a capacitor here, how many poles you get it? Yeah, but then in the Miller's approximation, actually, because you are splitting and then doing like this, you think there are, instead you find 2 poles, not 1 pole. But then at the cost of, not complex, maybe at the cost of simplicity. Because you are making it simple, but then you are paying a little bit price. Then, so that is most, then as I said, in the output, you see some capacitors. Then why Miller's theorem is relevant? Why do we have to take into account the capacitor in your amplifier? Sorry, not in the amplifier. Yes, in the amplifier, but maybe the fundamental quantity will be capacitors in the MOS transistor or BJT transistors. And then this capacitor may be coming from, when you have output capacitor, maybe from a load. But then this input capacitor may be come from between gate and source. And then this floating may be between drain and gate. MOS, so we are going to take MOS first. MOS intrinsic capacitances. What do you mean by intrinsic? Intrinsic means that is inbuilt, not that one you connected, intrinsic. So in the MOS you can see, when you take, this is NMOS or PMOS? NMOS, because this is a P substrate and then N plus doping. In the NMOS, here you already got a capacitor actually, because you got a gate, then you got another substrate, then you got a oxide layer. So this here you already got a capacitor. So between this, here you got a capacitor, that's a big capacitor actually. But then you also got a capacitor here. Why? Because here you got a potential. That potential, then here you got a dielectric. Yeah, so here you form a capacitor. Then you also form a capacitor like this, because here you got a voltage. That voltage is different from this voltage. So then there will be a small effect like a fringing capacitor or fringing field capacitor. A capacitor is formed due to fringing field. So whenever there is a voltage difference between 2 points, and then you get a capacitor effect actually. And then if it is not in parallel, like when you have two capacitors means if both are like in aligned, like both are coming like two potential difference, both are aligned, then you can say in between you got a capacitor. But even if it is a bit shift, what will happen is the electric field can positive, it can come to the negative. So that is called a fringing field. So this is a fringing field, a capacitor due to fringing field. Then gate oxide capacitor, that's a capacitor. And then here also you form a capacitor because you got N plus doping here, then you got another P substrate here. So you got a capacitor here, you got a capacitor here. And then reverse biased source bulk capacitance. Reverse biased drain bulk capacitance. Why it is reverse biased? Because here you got this is a P substrate, and then here you may be grounding. And then P substrate, usually substrate will be grounding. So that is the reason it's a reverse biased source bulk capacitance, reverse biased drain bulk capacitance. This is called overlap capacitance from gate to source or drain, because this is applicable here as well. This overlap region between gate and the drain. Here gate and the source. Overlap capacitance. This capacitance due to fringe field lines between the edge of gate and the top of the source bar drain region. So this is called a fringing, because here is not in line, but still electric field will go from positive to negative when there is a potential difference. So that is this capacitance is called fringe field lines. The electric field can from, if it is positive, this is positive, more positive, this is less positive, this is more positive, then the field will be like this. Field will be from positive to negative, or more positive to less positive. And then this is due to fringing field. Then capacitances, one between the gate and the channel, called gate oxide capacitance, given by WL into COX, and two associated with the reverse biased source bulk and drain bulk junction. See these two capacitors. For a MOS, there exist oxide capacitance from gate to channel, junction capacitances from source bar drain to substrate, and overlap capacitance from gate to source drain. See, so you got more capacitances. Capacitance from gate to channel, because this is a capacitance from gate to channel. Then junction capacitances from source drain to substrate. See from here, and then overlap capacitance from gate to source drain. So I want to highlight junction capacitances from source drain to substrate. What do you mean by source drain to substrate? See, source drain to substrate. So that is these capacitors. High frequency model of transistors. So far we have not taken into account high frequency. Now we are going to discuss about high frequency model of capacitors. Then at low frequencies, what will happen to these capacitors? Yeah, so impedance equal to 1 by 2 pi fc. So when your frequency is very, very small, tends to 0, what will happen is impedance is infinity. When impedance is infinity, then what will happen? This capacitor is open, this capacitor is open, impedance. So you don't have any effect of these capacitors. So that is the reason in the small signal, in the previous case, we did not take into account these capacitors, because those are low frequencies. We don't have any effect. But then when you take these MOS transistor, or in general transistor at high frequency, all these effects will come. That is called high frequency. High frequency. Yeah, that's a good question. So for a person who worked in high frequency, like I worked in high frequency electronics in the beginning of my career. So for me, high frequency is above 1 gigahertz. Yeah, why I say 1 gigahertz is, you take a transistor, then you pump the different frequencies, and then you plot the frequency response. All the major effect, these parasitic things will come into a picture after 1 gigahertz, around 1 gigahertz. You will be surprised to see how your signal attenuated. Like you take a BJT, and then you see bandwidth, maybe these days you can easily find around 500 megahertz bandwidth. Easily you can find out. But then you design the amplifier, then you pump the signal. Okay, 500 you are getting nice signal, then 600 you will see a little bit problem started maybe attenuating the output. But once you around 1 gigahertz, you will see a big effect, because all these parasitic capacitors in the transistor will come into account. Not only these parasitic capacitors, your capacitors parasitic effect in the PCB. Whenever you got the PCB also got these parasitic components, all these things will come into picture at high frequencies, around 1 gigahertz. So that is high frequency. So, but then we have to study high frequency effect. Why? Because your processor in your mobile phone, all these are operating in gigahertz frequencies. And then people are much concerned about capacitor value in your transistor. So transistor model does not contain a channel, because the problem is how will you take into account these transistors? How will you take into account these capacitors? Means your capacitor. So our aim is you got these capacitors, but then you got a transistor symbol. But then how to put these capacitors around that symbol? So what I'm talking is you got these capacitors, this high frequency. In order to get high frequency model, we need these capacitors. But then the question is when you have these capacitors, somehow we need to represent it. Like you got your symbol is, your MOS symbol is, for NMOS, it is like this. Then this is your gate, this is your drain, this is your source. Then the capacitor, here you got the capacitor between gate and source, easily you can represent. Capacitor between drain and source you can represent. Gate and source you can represent. But then there is a problem here. How can you model? Transistor model does not contain a channel, because now you got a capacitor that is between gate and channel, not between gate and the drain, gate and the source. How will you get it? So gate oxide capacitance is, so in order to represent that in the model, so gate oxide capacitance is decomposed into one between gate and the source and another between gate and the drain. So what we are telling is you got this capacitor that is between gate and the channel. But then this we can't represent in the transistor symbol. Why? Because we can't draw it with the channel inside. If you are not then you might ask why I don't want to represent it in the circuit. If you don't want to represent it in the symbol, you may have trouble when you draw the small signal. And then it is easy if you can represent in the symbol, so we get much more insight. Then what they will do is you got this capacitor, then they will split this capacitor between one between gate, this capacitor, so this is splitting, and then one between this point and here, source, and then one point between and then gate. So then what we will do is we will say that is equal to C1 plus C2. Now you got two capacitors, means this point and here, this point and here. So this point and drain, that is C1, gate and the source, that is C2. So then you have taken into account the capacitance between gate and the channel. Now when you do that one, we got this capacitor. See, I have drawn it. So this one is what we split into two, because we can't represent the channel in the symbol. So we need to represent this capacitor in the channel, so that this we split into two. So when you split into two, then we have taken into account all these capacitors. So this is C1, this is C2. Then this is a gate. And then between gate and the drain, this is CGD. Capacitance between gate and drain. This D means dB, means the capacitance between drain and the, what is B? Is it oxide layer? Bulk is here, the substrate. And then this one, source and the substrate, so we call bulk. Then between gate and the source, the gate oxide capacitance is often partitioned between source and the drain. In saturation, when you are operating your when you are operating your transistor in the saturation region, we are talking about saturation because this is a MOS. MOS saturation is you are operating in the amplifier. As an amplifier, when you are operating MOS in the saturation region, your C2, that is the capacitance between gate and the source C2, that is due to the channel, which can approximately equal to your gate capacitance. And then C1 between drain and the gate, so that will be approximately equal to 0. So that is experimentally noted. They are in parallel with the overlap capacitance to form CGS and CGD. Why? Because what it says is you got this capacitor that is between gate and the channel, but then because we can't represent the channel in the symbol here, the capacitance value we can't represent here, we will split it. So we take this point gate with respect to source. So you got this capacitor here, then gate and the drain, you got another capacitor here. But then this capacitor is coming in parallel with the capacitor here because you got this capacitor. And then this capacitor is coming in parallel with these two, see, this capacitor. So that when you are operating at saturation, what it says is your C1, the C1 will be almost 0. Then C2 will be approximately equal to your gate capacitors. So then we can combine. Then what we'll do is we can combine these two coming in parallel. So when capacitors coming in parallel, you add up. And then you represent as, so here CGD, that is between gate and the drain. And then gate and the source. See, gate and the source. So then gate and the source, CGS already got gate capacitance in parallel with your C2. But then here between gate and drain, you got the capacitance between gate and drain, but then it is coming in parallel with the C1, but then C1 is almost 0 when you are operating the saturation. So then we take that saturation value because that is important for us because we are using as an amplifier. They are in parallel with the overlap capacitance to form CGS and CGD. So when you draw the small signal gate, then the capacitor between this point and then the source. See, this point and this source. And then maybe I'll draw it. Maybe you can draw together. It's not that complicated. So when you have this, you got the MOS. Yeah, here anyway I got the MOS. So then here what you have got is a capacitor that is called CGS. And then this is source. And then you have got another capacitor that is equal to CSB, source and the bulk. Bulk is your substrate. Then you also got another capacitor here. What is that value? CGD, capacitance between gate and the drain. Then you got another capacitor here that is equal to your CDB, drain and bulk. So when you draw the small signal, it's very simple. So you got the gate. And then you can draw like this is open, positive, negative because this point. And then you got the ground. But then between gate and the source, you got a capacitor. So that's the reason this capacitor, between gate and the source, you got a capacitor. But then your ARPA is open. So this is CGS. Then this point, that is your source. Then from the source, this point, what is happening is, then you got already another capacitor, CSB, that is going to the ground. So that is the reason from here, CSB, source and the bulk, there is a capacitor effect. Then between source and the drain, you got the current source. Then what happens? Then you got RO. You have to take into account your channel length modulation. Then this is a drain. So from drain, you got another capacitor that is between drain and the bulk, your substrate, CDB. Then you also got another capacitor between drain and the gate. So that is the reason we got another capacitor that is a drain and the gate, and then which is equal to CGD, gate and the drain. Then this is a high frequency small signal model. So this is called high frequency small signal model of MOS transistor. So you can draw similar to BJT as well, transistor. So maybe in the Intel, IBM, they will discuss about the high frequency model because they are not interested in the low frequency model. Then what will happen is in the capacity impedance, low frequency, what will happen? In the low frequency, the impedance equal to 1 by 2 pi f into C, f tends to 0. Then what will happen? This capacitor will be open. This capacitor will be open, high impedance. This capacitor will be open, this capacitor will be open. So you get your normal small signal, that is your gate when f tends to 0 using this expression, then C's will become open, means impedance, so that you don't have to take into account. So then you get your low frequency one. So you got the positive, negative, then you got the ground, then you got impedance, then you got RO. So this will collapse to this one when f tends to 0. You know what I meant? So that is the reason in the low frequency we don't have to take into account these capacitors. High frequency, yes, we have to take into account these capacitors. So find coupling capacitors, group work. Then we discussed about intrinsic gain. How many of you remember intrinsic gain? Okay, so what is intrinsic gain? Yeah, so then you have to answer my question. Somebody gives you a transistor, maybe a MOS transistor, and then will ask you two questions. What is the maximum gain you can get? What is the maximum frequency you can operate? So you should be able to answer these two. Then what is the maximum gain you can get, which we already studied, that is called intrinsic gain, which is equal to minus GM into RO. That is for a common source amplifier, minus GM into RO. That is called intrinsic gain. You can't say that, oh, depending upon all the design, no, that's not correct. The intrinsic gain is minus GM into RO. Next question, what is the maximum frequency you can operate? Then we have to find out. So the maximum frequency that you can operate is depending upon your high frequency model. Why? Because, so from here, you got the capacitors, as I said, in the low frequency, you get a low frequency gain minus GM into RO. But here the gain is a bit more complex. You have to take into account the capacitors. Then, why these capacitors, usually people call it as a parasitic capacitors. We use the parasitic term because this is kind of a killer when your frequency is increasing. This parasitic, which we don't like, killing your signal at high frequencies. Then, I design one transistor, maybe you design one transistor, then we give it to someone. Then you got two transistors, one I designed, one you designed. Then we are asking him the question. Then he might ask us the question. Okay, I have two questions. What is the maximum gain? Then we both will say, yeah, that is an intrinsic gain minus GM into RO, depending upon your channel length modulation. Yeah, frequency. That's the reason the whole point is the frequency, that frequency response. No, but intrinsic gain is the intrinsic gain. Okay. Yeah. That gain, yeah, definitely, because that's the reason we plot the frequency response. So that's the reason we need the two questions. So that's the reason I'm coming to that point. So first we answered minus GM into RO intrinsic gain, and then that's depending upon GM into RO. See, minus GM into RO. And then this RO is the channel length modulation due to that one, or early effect for BJT. But then this minus GM will have that factor, your frequency factor. Yeah, we will do that one. Yeah, then when you combine only you get to the exact gain. Then why the gain is different? Like you designed one, I designed one. The gain is, the maximum frequency of operation will be different. Why? Because it's depending upon the capacitor values. Because even if we both got the same RO, if we get these capacitors different, means what you designed got another frequency cutoff, what I designed got another frequency cutoff. For example, if these capacitance are very, very small, like in picofarads, then what will happen? Very, very small. Then this will be kind of shorting all your signal. So that is the reason, it's depending upon the capacitor value. So we can define a maximum frequency that is called a transit frequency. So that is the ultimate speed of the transistor, means maximum frequency at which you can operate the transistor. Then how will you define it? The transist frequency means you connect 1 volt here. 1 volt is maybe a bit more amplified version, see, but for an example, exaggerated version. So if you get 1 volt here, if you get maybe gain X volt, that is your output here, what you are seeing, and then X, your X volt is greater than 1 volt. But then you increase the frequency. When you increase the frequency, when this 1 volt, then your output also is 1 volt, then that frequency is called a transit frequency for this one. You know what I meant? Because after that there is no point in increasing frequency, then what you are getting is output less than input, the voltage. You are attenuating. So then when input equal to output, input voltage equal to output voltage, that frequency is called a transit frequency. Because that is a definition. Means your gain equal to 1. Because below that, there is no point in getting some attenuation. We will not call it as an amplifier. So transit frequency is the frequency at which current gain equal to 1. With various capacitances surrounding bipolar and MOS devices, is it possible to define a quantity that represents the ultimate speed of the transistor? Transit frequency is defined as the frequency where the current gain from input to output drops to 1. I discussed it. So, sorry? No, because the transistor, so the fundamental quantity is current. We are amplifying the current. So that's the reason that we are taking into account current. Because when you talk about voltage, how can you get voltage from a transistor alone? Because transistor, what you get is output collector current. You are getting a voltage because you are connecting a resistor, and then you are converting current into voltage. Yeah, so then this is a BJT. For BJT also you will find capacitors. So between base and the collector we call it as C mu. Between base and the emitter we call it as C pi. C pi makes sense because this is R pi. And then this is a C S into S. Collector and the bulk substrate. So then from here we can write I out equal to Gm into V in, because your output current equal to transconductance times your input voltage. I out equal to Gm In into Z in, because that is again depending upon input current into input impedance equal to V input, because whatever the impedance is coming. Then we can write Zin, what is the input impedance? When you look at here, you got impedance of the R pi in coming in parallel with the C pi here. You know what I meant? Because R pi is between base and the emitter, so these two are coming in parallel. So then you can write down I out by I in by substituting Z in here, then you get this value. You can represent Gm into R pi equal to Gm equal to beta by R pi. So cancel out beta by, and then what you can do is you can take modulus and square it, and then equal to 1, because this I out by I in equal to 1, that is the transit frequency. So that is the reason you are getting this one, and then you can find out omega t, because this is omega t, which is equal to Gm by C pi for the BJT. So that is a transit frequency. So 2 pi f is equal to omega, which is equal to Gm by C pi. And then, so we neglect Cu and CCS because that effects are negligible compared to this one. Maybe I'll stop here and continue in the next lecture.